Hi everyone. Okay, so in this video, I'm going to talk about the Fourier transform's properties. And so I have two tables here. Let's look at this one first. Oh, it's cut off on the screen. Okay, there. All right, so this table lists all the properties of the Fourier transform. And so you can use these properties to rewrite whatever equation you're trying to solve for the Fourier transform and make it easier to solve it. So this is the list of them. Now let's look at this one, which it's going to be really difficult to fit on the screen. Okay, so these are the Fourier transform pairs, which means if your inputted signal, which is in the time domain, is on any of these functions on the list, then it lists its Fourier transform. And so that's really convenient because then you don't have to go through the whole process of the solving it, doing the integral, and all that stuff. So let's do an example using both these tables. How can I fit? Okay, let me write the example down and then I'll scroll back it up. Let's do, example. Let's find the Fourier transform of f of t equal 1 minus e to the negative b bt u of t. Okay, so let me see if I can fit it all. Let's see. I'm going to rewrite this function so that it looks more like something on the table. So what I'm going to do is distribute that u of t. So it becomes u of t minus e to the negative bt times u of t. Okay. So now with that, I can use since we have two functions being subtracted, which is basically adding a negative of a function, we can use this property right here. Where I'm going to call f1, oh, that's f1 equals u of t. So this first part, and f1 of t. f1 of t. And f2 of t, I'm going to call the second part, e to the minus bt u of t. And so now all we have to do is find the Fourier transform of each one of them. So, no. All right. We're going to fit the screen. Actually, I should probably write it. No, it'll fit. Okay. f1 of omega equals. So I have u of t. I don't want to do the integral. So I'm going to check this table, see if it's on the table. Where is it? Okay, here it is. It's right here. U of t. So that means I can just write, what was it? Pi delta omega plus, I have terrible memory, 1 over j omega. 1 over j omega. And then let's do f2. Should be here. I think it's, yes, this one. I just lost it. Wait. Oh, here it is. Okay. Oh, put it in a different color. This one right here. So that becomes oops, I want that to be white. F2 omega equals, I forgot it already, 1 over b plus j omega. But there's a constraint. The real part of a, or in our case, b, which is the coefficient in the exponent, b has to be greater than 0 in order for this to be true. So, given our linearity property, which is this one, we could just add up the Fourier transforms of the two functions. So, I need to make sure I can fit the screen. Okay, so f omega ends up being f1 omega minus f2 omega. We have the negative because it was, let me highlight it, originally negative. So then that becomes pi delta omega plus 1 over j omega minus 1 over b plus j omega. And I'll simplify this more to be, is everything fitting on the screen? Pi delta omega plus, b all over minus omega squared plus jb omega. There we go. And that's an ugly W. Okay, there you go. And that's how you use these two tables to quickly solve the Fourier transform. Because if we had done it the other way and putting it to the integral, it would have taken a lot longer. And once you start using the properties and transform pairs more often, it'll be even more quicker. So that's it for this video. Thanks for watching. See y'all next time.